In this segment, we'll look more closely at how bits behave during binary addition and subtraction, and at how the CPU tests for various arithmetic conditions based on that behavior. Earlier lectures introduced the CMP operation, followed by tests based on the result of the comparison performed by CMP. This instruction pair, for instance, assigns R2 into R1 only if R2 is greater than R3. Now that we've got more knowledge of binary arithmetic, and have kept our binary 8-bit and 16-bit ranges here just for reference in the diagram, now that we have that knowledge, let's look more closely at just what CMP does, and how the results of its comparison are recorded by the CPU. The short answer is CMP performs a subtraction. It's like a sub, but without saving the result. What it does save, however, is whether the result was a 0 or not, and whether the result was negative or not. These two true-false values are stored in something called the Program Status Register, or PSR. Earlier lectures promised more registers than just R0 through R15, and the PSR is the next one, as shown by the arrow here. The PSR doesn't store a single number like the other registers. Instead, each of its 32 bits has a specific purpose. Two of those 32 bits, termed the N and the Z flags, I'm going to expand its size here so that I can get more bits in there. So there are the N and the Z bits in the PSR. These represent whether the most recent CMP result was a 0, that's the Z flag, or negative, the N flag. An assembly instruction that is conditioned on the results of an earlier CMP checks the PSR bits and executes or doesn't execute based on their state. ARM assembly uses a pair of letters after the assembly opcode to indicate this, so move GE is a move conditioned on a greater than or equal outcome. Many other two-letter conditions are allowed. Move EQ, for instance, would do a move only if the compared values were equal. And question 1. Given that CMP performs a test subtraction on its arguments, what combination of N and Z flag values would make a subsequent move EQ instruction execute? Well, the answer is that R2 would have to be equal to R3 if the test subtraction produced a 0 result, so the Z flag needs to be 1. There are two more PSR flags that result from arithmetic operations, and they both deal with overflow conditions during addition and subtraction. Overflow occurs when addition or subtraction produces a value that is beyond the range of the integer in question, either too high a value or too low a value. A too low value doesn't sound like an overflow, but it's still called that. It's useful to consider how overflow happens and is detected in both signed and unsigned cases. Let's do that, sticking with the easy-to-discuss 8-bit case. In practice, integer operations are almost always at least 16-bit or higher, but the 8-bit example extends easily to larger ints. Let's start with overflow for unsigned 8-bit ints, as I've done with a little better diagram here. Recall the allowed range for such ints from 0, all zeros, to 255, all ones. And then question 2 here. Recall the earlier discussion on modular arithmetic. In 8-bit arithmetic, 256 wraps back to 0 like the arrow shows. So what value do we get if we add two unsigned 8-bit ints with values, say, 220 and 50? Think about it. 220 plus 50 is 270, and that's too high. So it wraps around. And since 256 wraps back to 0, 270 wraps around to 14. And so in unsigned, what we would get then is that 20 plus 50 equals 14. Overflow in unsigned ints happens when the value wraps back like that. If this happens, the CPU sets a PSR bit called the carry flag. Now, to understand why it's called that, consider the decimal car example from earlier lecture. What would happen if we added 600,000 and 500,000 on that odometer? which of course would result in overflow. If we did that kind of addition, we'd end up with zeros in most of the positions. So we'd have all zeros for the last 5 positions. And when we added the 6 and the 5, we'd end up with a 1, and we'd carry 1 into the millions place. So that carry is the interesting thing. The odometer doesn't have a millions place, so the carry is simply lost. In fact, this is how the wraparound occurs on the odometer, by dropping anything carried into that non-existent millions place. We haven't discussed binary addition in this class. It's more of a hardware topic, but the process of adding place values and carrying the excess into the next place happens during binary addition in much the same way as in decimal addition. The carry just happens when the sum of bits exceeds 1 instead of when the sum of digits exceeds 9. And when a carry occurs when adding the MSBs, that indicates a wraparound, just as in the car odometer. The carry flag is set when a carry occurs from adding the MSBs, thus its name. There is, however, another case to consider: subtraction. If we subtract a larger unsigned value from a smaller one, that also involves a wraparound 0, but in the downward direction. And how does the CPU detect this? So question 3, back to the car odometer. What value would we get on the odometer if we did a subtraction of 2,000 from 1,000, like I've set up here in the diagram? And what would the borrowing look like in such a subtraction? Would anything be borrowed at the millions place? Try it by hand, subtracting the 2,000 from the 1,000 using the usual grade school procedure. Well, the answer is that we would wrap back around 0 in the opposite direction, arriving at 999 all zeros. So we'd have a 0 here, and here, and here, but 1 minus 2 would, of course, require a borrow, and we'd have a 9 with a borrow of 1, thus 9 minus 0 in the next one, and 9 minus 0 in the next one, and we'd end up with a borrow in the 100,000s place, so we would be borrowing from the millions place. In the odometer, overflow is indicated, subtractive overflow is indicated by borrowing in the leftmost digits. And in the binary case, subtractive overflow is indicated by a borrow when subtracting the MSBs. The carry bit is also set when this happens, and it thus covers both types of overflow. It should probably have been called the carry/borrow bit. Okay, so the carry bit covers any case of unsigned overflow. What about overflow for signed values? Well, question 4 here. Considering how 2's complement works, is wrapping around 0 necessarily a problem when adding signed values? And if not, in what case is it okay? Well, the answer is that wraparound is how 2's complement works. In particular, adding a negative to a positive always causes wraparound, and it should. So then question 5. If passing or wrapping around 0 is okay in 2's complement operations, what is not okay? Assuming 8 bits, what boundary must the operation not pass? The answer is that it cannot pass the breakpoint between positive and negative. I'll fill in signed values and clear the diagram up a bit, and that red arrowed breakpoint is the boundary that a signed addition or subtraction should not pass. If we are adding, say, 5 and minus 2, we'll wrap around to 3, and that's fine, going around 0. But we cannot cross this boundary without an error. For instance, if we, in signed values, added 150, that'll result in the pattern or bit combination that would be interpreted as 150 unsigned but is actually about where that red arrow is sitting in the range, and think about it carefully, is a minus 106 instead. And that's what happens when you cross that boundary. So how do we know whether the operation crossed it? Well, question 6. Can that boundary be crossed? Can overflow occur if we add a positive and a negative? The answer on that one is no. The sum of a positive and a negative must lie between the two operands and thus cannot be out of range. So to get overflow across that middle range boundary, we need to add two positives or two negatives. Putting that differently, the MSBs of the two operands must be the same for an overflow to be possible. All right, so what kind of result do we get from signed overflow, assuming the same MSBs? Say we add two 8-bit positive values like 120 and 110. They'd sum to 230 in unsigned form, but what is that in signed form? And then answer the same question for adding negative 120 and negative 110. If you do the math and the modular arithmetic correctly, 230 in unsigned form is minus 26. And negative 120 and minus 110 sum to negative 230, which is the same as positive 26. So even adding, to take an extreme case, minus 128 and minus 128 results in 0, not a negative value. And adding 127 to 127 results in minus 2, not a non-negative value. So the acid test of signed overflow is that the two added values have the same sign, both either negative or positive, but the result has the opposite sign. This condition is what the PSR V flag detects. V is for overflow. Okay, so now we have both the C flag for going across the 0 boundary and the V flag for going across the minus 127, negative 128 boundary, or actually whatever the 2's complement boundary is for the values being added. 32-bit edition sets the V flag if the result crosses the, take a breath, 2,147,483,647 versus minus 2,143,483,648 boundary, for instance. How does the CPU know whether we're doing signed or unsigned math? There aren't different assembly languages, or assembly instructions, I'm sorry, for the two forms. It's all the same hardware doing the same operations. Remember, the distinction between signed and unsigned is just a viewpoint. So the CPU sets both C and V flags, and it's up to us to choose which one to test if we want to know whether there was an overflow. Such tests are sometimes done at the assembly level, but most compiler-generated assembly leaves it up to the programmer to be sure no overflow occurs, since the overhead of testing every operation would slow down the program. That's one reason for knowing the symptoms of overflow. If you add two unsigned values and get a smaller unsigned value, or if you subtract unsigned values and get a larger unsigned value, that's arithmetic overflow. And likewise, if you do add operations on two positive signed values and get a negative value, or vice versa, then that's overflow.